Module 3, Section 2.4, Polynomial and Rational Functions. Objectives. Objective 1. Define and identify properties of polynomial functions. Objective 2. Define and identify properties of rational functions. Objective 3. Application problems. Objective 1. Polynomial functions. Definition. A polynomial function is a function that can be written in the form a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 plus etc. plus a sub 1 x plus a sub 0 for n a non-negative integer called the degree of the polynomial. The coefficients a sub 0, a sub 1, etc. a sub n are real numbers with a sub n not equal to 0. The number a sub n, the coefficient of the variable to the highest power, is called the leading coefficient. The domain of a polynomial function is the set of all real numbers. Characteristics of polynomials. Graphs of polynomials are continuous with no holes or breaks. Graphs of polynomials usually have turning points, which is a point that separates an increasing portion of the graph from a decreasing portion. If f of x is a polynomial of degree n, then the graph of f has at most n minus 1 turning points. If f of x is a polynomial function, then the values of x for which f of x equal to 0 are called the zeros or solutions of f of x. Each real zero appears as an x-intercept of the graph of the polynomial function. The graph of a polynomial function of degree n will have at most n x-intercepts. Example, for the given polynomial function, find the degree of the polynomial. When we expand this function, we get 28x square minus 26x minus 24. The degree is the highest power, which is 2. So the degree is 2. To find the x-intercept, put 4x minus 6 is equal to 0 and 7x plus 4 is equal to 0 and solve for x. 4x minus 6 is equal to 0 gives x equal to 3 by 2 and 7x plus 4 is equal to 0 gives x equal to negative 4 by 7. So 3 by 2 and negative 4 by 7 are the x-intercept. To find the y-intercept, substitute x equal to 0 in the function. 4 times 0 minus 6 times 7 times 0 plus 4 gives negative 6 times 4, which is equal to negative 24. So the y-intercept is 0, negative 24. The leading coefficient is the coefficient of the highest degree term. Here it is 28. So the leading coefficient is 28. Example, for the given polynomial function, find the degree of the polynomial. Degree of the polynomial is the highest power. Here it is 2. So the degree of the polynomial is 2. To find the x-intercept, put negative 2x square plus x equal to 0 gives x square is equal to 4. Take square root on both sides. X is equal to plus or minus 2. So the x-intercepts are 2, 0 and negative 2, 0. To find the y-intercept, substitute x equal to 0 in the function gives y is equal to 8. So the y-intercept is 0, 8. The leading coefficient is the coefficient of the highest degree term. Here it is negative 2. So the leading coefficient is negative 2. The leading coefficient test. As x increases or decreases without bound, the graph of the polynomial function f of x is equal to a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 plus etc. plus a sub 1 x plus a sub 0 eventually rises or falls. If the degree of the polynomial is odd and the leading coefficient is positive, the graph falls to the left and rises to the right. If the degree of the polynomial is odd and the leading coefficient is negative, the graph rises to the left and falls to the right. If the degree of the polynomial is even and the leading coefficient is positive, the graph rises to the left and to the right. If the degree of the polynomial is even and the leading coefficient is negative, the graph falls to the left and to the right. Example, the given graph is a graph of a polynomial function. What is the minimum degree? Minimum degree is 3 because there are 2 turning points or 3 x-intercepts. The leading coefficient is negative because the degree is odd and the graph rises to the left and falls to the right. Example, the given graph is a graph of a polynomial function. What is the minimum degree? The minimum degree is 4 because there are 3 turning points. The leading coefficient is positive because the degree is even and the graph rises to the left and to the right. Objective 2. Rational functions. A rational function f of x is a quotient of two polynomials n of x and d of x for all x such that d of x is not equal to 0. Example, let n of x is equal to x plus 5 and d of x is equal to x minus 2, then f of x is equal to x plus 5 divided by x minus 2 is a rational function whose domain is all real values of x with the exception of 2. 2 is not in the domain because the function becomes undefined when x is equal to 2. Vertical asymptotes of rational functions. X values at which the function is undefined represent vertical asymptotes to the graph of the function. A vertical asymptote is a line of the form x is equal to k which the graph of the function approaches but does not cross. In the figure below, which is the graph of f of x is equal to x plus 5 divided by x minus 2, the line x is equal to 2 is a vertical asymptote. The domain is all real numbers except 2. Horizontal asymptotes of rational functions. A horizontal asymptote of a function is a line of the form y is equal to k, which the graph of the function approaches as x approaches to plus or minus infinity. For example, in the graph of x plus 5 divided by x minus 2, the line y is equal to 1 is a horizontal asymptote. Generalizations about asymptotes of rational functions. Consider the rational function f of x is equal to n of x divided by d of x, where n of x and d of x are polynomials. Vertical asymptotes. Case 1. Suppose the numerator n of x and the denominator d of x have no real 0 in common. The line x equal to c is a vertical asymptote if d of c is equal to 0. It means to get the c values, set the denominator d of x is equal to 0 and solve for x. Case 2. If the numerator n of x and the denominator d of x have one or more real zeros in common, cancel the linear factors, then apply case 1. Horizontal asymptotes. Case 1. If the degree of the numerator n of x is less than the degree of the denominator d of x, then y is equal to 0 is the horizontal asymptote. Case 2. If the degree of the numerator n of x is equal to the degree of the denominator d of x, then y is equal to a divided by b is the horizontal asymptote, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. Case 3. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Example. For the given rational function f of x is equal to 6 minus 3x divided by x minus 5, find the vertical and the horizontal asymptote. To find the vertical asymptote, set the denominator is equal to 0. X minus 5 is equal to 0 or x is equal to 5. So x is equal to 5 is the vertical asymptote. Horizontal asymptote. Here the degree of the numerator is the same as the degree of the denominator. So the horizontal asymptote y is equal to the leading coefficient of the numerator, which is negative 3, divided by the leading coefficient of the denominator, which is 1. So the horizontal asymptote is y is equal to negative 3. To find the x-intercept, put the numerator 6 minus 3x is equal to 0 gives x is equal to 2. So the x-intercept is 2, 0. To find the y-intercept, substitute x equal to 0 in the function gives y-intercept minus 6 divided by 5. So the y-intercept is 0, negative 6 divided by 5. Determine the domain. The domain is all reals except x is equal to 5. 5 is not in the domain because the function becomes undefined when x is equal to 5. Let us use the calculator to graph the function. Go to y, enter the function as you see here. Push the graph. The graph looks like this. As you can see, x equal to 5 is the vertical asymptote. Example. For the given rational function f of x is equal to 2x divided by x minus 3. Find the vertical and the horizontal asymptote. To find the vertical asymptote, put x minus 3 is equal to 0 gives x is equal to 3. So x equal to 3 is the vertical asymptote. Horizontal asymptote. Here the degree of the numerator is the same as the degree of the denominator. So the horizontal asymptote is y is equal to the leading coefficient of the numerator, which is 2, divided by the leading coefficient of the denominator, which is 1. So y is equal to 2 is the horizontal asymptote. To find the x-intercept, put 2x is equal to 0 gives x is equal to 0. So 0, 0 is the x-intercept. To find the y-intercept, substitute x equal to 0 in the function gives y is equal to 0. So 0, 0 is the y-intercept. The domain is all reals except 3. 3 is not in the domain because the function becomes undefined when x equal to 3. Graph the function. The graph looks like this. X equal to 3, that is the vertical asymptote. Y is equal to 2, that is the horizontal asymptote. And 0, 0 is the x-intercept. And 0, 0 is the y-intercept. Application problem. Example. A company is planning to manufacture snowboards. The fixed costs are $200 per day and total costs are $4,600 per day at a daily output of 20 boards. Assuming that the total cost per day is linearly related to the total output per day x, write an equation for the cost function. We know that the total cost is equal to fixed cost plus variable cost. So we can write C of x is equal to a plus bx, where a is the fixed cost and b is the cost per unit and x is the number of units produced. It is given that the total cost is $4,600 and the fixed cost is $200 and x is equal to 20. We need to solve for b. Substituting the values in the function gives 4,600 is equal to 200 plus b times 20. Subtract 200 on both sides gives 4,400 is equal to 20b. Divide both sides by 20 gives b is equal to 220. So the function c of x becomes 200 plus 220x. The average cost per board for an output of x boards is given by c of x divided by x. Find the average cost function. The average cost function is cx divided by x, which is equal to cx is 200 plus 220x divided by x. That is the average cost function. Sketch the graph of the average cost function including any asymptotes. We know that the average cost function is 200 plus 220x divided by x. Here the horizontal asymptote is y is equal to 220. Here is the horizontal asymptote, which is y is equal to 220. What does the average cost per board tend to as production increases? As you can see, the graphs get closer and closer to the horizontal asymptote as x increases. The average cost per snowboard tends to $220 as the production increases.